Hexagon cloak, NASA star shine. Artificial fake sun, sky, and moon. Planet X Nibiru hiding because International Space Station's using their camera and showing it for some reason. Plot device patent number 32 yada yada and 33 yada yada, 1961 to 1960 something else. Yeah, that looks like it. There's your evil death ray. And it's hexagons because there's a hexagonal storm on Jupiter. There's also an eye-shaped storm, but people have stopped trying to make that the eye of the all-seeing one, because that would imply we were Jupiter worshippers or something. No, 100% can't debunk it. What is this thing really? I want you to look at the shape. It may be flat, it may be parabola, maybe a parabolic shape. It's a hexagonal shape. And in case you didn't know this, hexagons, like triangles, are sacrosanct in engineering because they have certain characteristics that make them more stable. Next. This was a patent from 1966, probably a second patent. That's the one that ends in 660. On the left you see the whole array. The bottom, Fig 1, there's a light source of some sort that's aimed at a mirror, and the light goes through and bounces off of all sorts of things here to get to here. This is number 28. It's apparently a lens. It's focused on this, that spreads it out more, and then it hits these, and then that's supposed to do something else. The idea is to get the light rays to be parallel with each other, because light sources tend to make light go out in all directions. The sun, however, is so far away that the light comes in almost perfectly parallel. So this is an attempt to make a parallel light source. On the right you see the light source itself diagrammed out. You'd have to go through the whole patent, but basically these three objects here are the light sources. They're halogen lights. Bounces off of these reflectors. Here's a parabola, a parabolic reflector, and then where this stem comes through, it has reflectors here to try to get the light to come off and as much energy as possible go forward. And this is what it's supposed to look like on the front. Now we see hexagons. Why hexagons? Because circles, if you put them next to each other, leave gaps in the middle. Hexagons don't. Bees do it. You can do it. We all do it. Let's call the whole thing off. Okay, now let's go back to that image. Oh, there it is. Nobody told you on any of these videos showing this that this is at the Marshall Space Flight Center in Huntsville, Alabama. It's called the Solar Thermal Test Facility Concentrator Mirror. And it's got most of the mirrors covered there because they put on little, covers to make them to where it doesn't reflect as much light energy. That's a vacuum chamber at the focal point. The mirror beams 1 million watts of solar energy per square meter when all of the hexagon-shaped mirror segments are fully uncovered. And they may be parabolic. They may be parabolas. The idea with this is, instead of having one big mirror that will absolutely warp with temperature and whatever, or just not be perfect, make a bunch of really small, really well-made mirrors, and then make them all fit together, and then aim them at the same subject. Kind of like, trying not to fail. That's why they're hexagons. Yeah. Next thing. Reflectors versus lenses. Now on the lower left there you'll see Fresnel lens versus the standard lens. What you do is you take the segments of the lens that are important and you cut it in thinner slices and use those slices stacked together in concentric rings. Actually, they look all circly, like a bunch of bullseyes. And it has the same effect as a lens almost. It's not absolutely perfect. The distances aren't perfect. But you can also correct that to make a Fresnel lens almost, if not absolutely perfect. The main advantage with them is they're more like a sheet of glass. You can etch them into glass. You can mold them easier. And because their thickness is more consistent, they don't warp as much. Sounds familiar, right? And then there you can see the thickness comparison. And then to the right of it, right in the middle, is something I concocted a long time ago. When I was a kid, I got a hold of a Fresnel lens from a toy lighthouse. Not a toy outhouse, a toy lighthouse. Now, I wanted to make a copy of it, and I was a dumb little kid, so I decided I was going to mold the copy of the part that actually did the work, which was that rough edge on the back. I also didn't like that it kept getting dirt in it, so I cleaned it really good, it was absolutely perfect, where you could really use it correctly. and then I sprayed it with a release material that was really, really fine. It was for making molds, and I wrapped tape around it, and then I filled the mold with something to try to copy it, and I didn't damage the mirror. In fact, in the process of pulling it out and turning it, because it acted like it was screwed together, it pulled apart finally, and in the process, the oil and the slightly abrasive material I used to make the mold made it look a little dull, so I ended up polishing it and made it even better. Then I realized I should have polished it beforehand. I put a release material on it and made a copy of the lens now directly, because I realized I couldn't really use the plaster Paris, and I made a copy by pouring clear plastic in it, because some dum-dum gave me access to that stuff from shop class. And when I got out, I made sure it was really thin, and then I ground it and flattened it, and I made that, and it wouldn't focus for nothing. However, when light bounced off of it, it made a hella bright spot in the middle of the air. It was a parabolic reflector converted to a parabolic Fresnel reflector. And on the right, you see an optical simulation using 20 elements. They're not squares. These are ring-shaped. Now, in the upper left, you'll see what's called I call it a linear lens. It's basically a big trough, and it's shiny, and light reflects off it. Now, cut it down the middle and drop the pieces on the ground so you don't get as much wind effect, and also so you can make it much more, again, mechanically stable and structurally rigid, and you end up with a Fresnel lens as a reflector, or basically a parabolic reflector that isn't big and bulky, and it concentrates the light just as well. And on the right, you see the same idea, only these are square segments. Because they're square segments, it's not really considered as good. As you can see, it's not as good a quality. It keeps duplicating things. But you can aim individual mirrors, and you can even use flat mirrors at this point. Now let's go back here to this. Here's Larry's Fresnel lens reflector, not lens, Larry's reflector Fresnel. Tie-dye. Yeah, Burning Man, where all the secrets of NASA are held. And yes, I can't tell if Larry's the guy on the left with a hammer or the pyromaniac on the right, but I decided to make fun of his tie-dye. Hey Larry, if you're watching this, you're now on my video, and well, I regret nothing. But this is an example of someone doing what's called a spiral cut mirror or something. It is actually a spiral. You basically get a really big sheet, cut a spiral in it, and then very carefully tighten it, and it turns into a parabolic shape, or it tries to, and it forms this kind of thing. Also, I should note, if you take a record player, put a bowl of water on it, or even better, a container of mercury, if you can do this safely, and spin it, the weight of the water will pull out to the sides and form, literally, a parabolic shape. None of these are really practical unless you need them for a specific thing. If you're in space, you need stuff to be mechanically consistent. You saw all that. Now let's talk about the NASA Sun Simulator, nicknamed STAR, to simulate the sun in space, but in a person-sized environment test chamber, like a box or room. On Earth, to test electronics, metal, plastic, glass, lenses. It's still done today with more modern methods and materials and light sources as a flat parallel illumination device. See also compact linear Fresnel reflector, and optical simulation of a parabolic reflector versus the 20 prism unit Fresnel reflector. Now let's review. This is not a death ray in space. It is not a fake sun. It is not somehow to cloak the sun. You can't send the polar opposite version of a light source back at it unless it has one optical frequency. You can cancel out red or blue or green from only one perspective, but you can't cloak a sun if it has more than one color to it. So it's not hiding Nibiru or some other damn thing, nor is the International Space Station involved in this. And again, everybody looking at their hexagonal images of light sources are looking at lens flares through a hexagonal light aperture. It's not always hexagonal. And if you want to change its appearance, rotate the camera on its axis, and your supposed hexagonal fake sun out there will rotate with it. Sounds like you can remote control something special. And again, nobody else sees this, so yeah. And here's the patent people keep bringing up because it's visually stimulating. Are you feeling stimulated or chocolated? Next. This is the real deal, and it's used on Earth. It uses sunlight because the sunlight comes in parallel. doing the exact opposite of what the patent does, so it's not associated with it. And again, no one tells you this is in Huntsville, Alabama, at the Marshall Space Flight Center, and no one tells you it's a solar thermal test facility concentrator mirror, using the mirrors to concentrate on a vacuum chamber to simulate the effects of being in space as far as heat. No one brings up the fact that this has been done to death on the ground. Even at Burning Man, the evil continues. And here's your text. Thanks for watching. Have a good day. Good luck with that. Bye.